Welcome to week 2 of the JSALT Summer School. I'm Jim Mayfield. You can guess which one of these. So I'm going to be doing the morning lectures, and then Eugene is going to be running the labs in the afternoon. And these slides are a compendium of many slides from many people, including these lovely people here. Hello. Hello. Will not advance. There we go. Yeah. I think it got confused over Zoom. Okay, so this is today's schedule. We'll have a little bit of talk about information retrieval, have a little break, have a little more talk about information retrieval, and then this afternoon in Malone, you'll have the lab with Eugene. So here's what we're going to cover. After introducing information retrieval, we'll talk about sort of 3 pieces of it: how information retrieval handles language coming in, how it does comparisons across pieces of text, and how it puts it all together in a system. So I hope we'll get through all of that this morning in the first session. And then if that works, in the afternoon, we'll talk first about how do we evaluate information retrieval systems, and then cross-language information retrieval, where you have queries in one language and documents in a different language. So what is information retrieval? It is the field concerned with the organization, storage, and retrieval of information. That information could be text, video, images, speech, anything like that. We're going to focus just on text today. And retrieving the other types of media is very important and is increasingly studied these days. But we're just going to focus on text because there's plenty there for us to take our time up. So as I said, there are 3 things we have to be able to do information retrieval. We have to be able to manipulate natural language, because we have text documents that have natural language, and we have queries that have natural language, presumably, and we need to be able to manipulate that language. And so that's done with things like tokenization and embedding. We need to compare information need that a user puts in somehow against the content of a document. That's done with things like cosine or approximate nearest neighbor search. And then we need to efficiently store and process the data using things like inverted indexes or vector stores. So these are the 3 bits we're going to talk about in order this morning. All right. To give you a sense for the kinds of tasks that are in information retrieval, there are actually many tasks that fall under this rubric, but sort of the main 3 are: first, keyword search, where you're trying to find documents that contain a single keyword, or maybe a Boolean combination of keywords. Like you type in kimchi, and you want your documents to have the word kimchi in them. Important thing about this type of search is it is a set retrieval search. That is, you're getting back a set of documents, but it's not ranked in any way. You just get this big blob of documents. The second one is what we call ad hoc querying. Given some information need that a person puts in, produce a ranked list of the documents in the order that the system thinks they're relevant. For that, we've used statistical systems until very recently. There are neural systems now that are performing better, but they're still inefficient. And one of the things about information retrieval is that efficiency has always been a big component of the study in the field, because we're dealing with very large amounts of data, and systems have to have reasonable response time. So information retrieval has always been, I think, more concerned with effectiveness, with efficiency, than other human language technologies. The third is text classification. This is sort of the inverse of ad hoc querying. In ad hoc querying, you have a fixed document collection, and your queries are changing. In text classification, you have a fixed query and your documents are changing. So maybe you have, you want to know about any adverse side effect on a patient taking Tagamet. That's the kind of thing where there'll be documents coming along as they're produced. And whenever there's one that's relevant, you need to set it aside. So that's a classification problem. We'll talk mostly here about ad hoc querying, the second one. So why is it hard? Well, there are actually quite a number of reasons that information retrieval is hard. But three of the big ones are these. Polysemy, so you have words that are ambiguous, like lead or lead, however you want to pronounce that first word, depending on the context, or John Major versus Major General John Kelly. Those are different uses of the same word major. And the problem is if you're querying on some word like bank, and you want to know about money banks, and it gives you back river banks, that polysemy is giving you difficulty. Second is synonymy. So you have different words that mean the same thing. And if you put in a query about a truck, and there happen to be documents about lorries, you probably like to get those back, even though you didn't say lorry. And third is morphology. There are a lot of word forms that you have to deal with. For example, juggle, juggling, juggle, jugglers. If you put in a query with any one of those words, you'd like to get documents that talk about the other ones too. But morphology is not particularly easy. In English, it's pretty easy. So there's simple things you can do for English morphology. But in other languages, it can be very difficult to deal with the morphology. Okay, so a lot of people think that information retrieval goes all the way back to the start of Google. And for those of you who are younger than Google, that's not surprising, but there's a very long tale of history on information retrieval. And there are four related historical lines. So there's the basic text search line. There's the application of computer science to it. There's the introduction of the World Wide Web. And then recently, the use of neural networks to do the retrieval. So we're going to talk about these four lines very briefly. Text search, we can probably trace it back to the Great Library at Alexandria, 300 years before the Common Era. And that library got pretty big, especially for the time. 700,000 volumes is pretty large. And you can imagine having to retrieve particular documents in that library when you don't have electronic systems. The next thing that comes along is the idea of a concordance. And a concordance is simply an index that maps from every word in the volume to where that word is used in the volume. Okay, so the 1230s, a concordance of the Latin Vulgate, which is a very early version of the Bible. In 1247, the complete concordance of the Bible was built. And then the way text was handled was created and changed. So we had the printing press come along, and then things like the typewriter that allowed creation of much more text than could have been created before. In 1872, 21-year-old Melville Dewey invented a classification system. Anyone know the name of that system? Just curious. Huh? Yeah, Dewey Decimal System, which is the way that books used to be stored in the library. So when I was a kid, there was no Library of Congress naming scheme for books. You used the Dewey Decimal System, and it was it worked okay. Library of Congress is better, but it was the way all the physical book libraries were set up for a long time. In 1890, an exhaustive concordance of the Bible, and I think it was King James, was built. And this is an example from it. So this is part of the Strong Concordance. And you can see that it has a bunch of different words. Here's the entry for study. And if you look at the first line, it says in Ecclesiastes 12:12, there is the use of the word study. And if you actually go and look at it, we see the word study there. Okay, so this was an exhaustive concordance. Every single word was indexed, including the. It also gave pointers back to the original words in whichever language they were going back to, which probably Hebrew. So this was a way to find information in this large volume. And we're going to reflect this notion of a concordance in a bit when we talk about statistical information retrieval. Computer science comes along. I guess in 825, we found out what an algorithm was. Skipping all the way to 41, that picture on the upper right is the Mark I computer. And that's probably some small portion of what's living in your watch now. In 1945, Vannevar Bush produced a very influential paper that essentially foreshadowed the World Wide Web. So he talked about this Memex device that would help you by doing retrieval over all the things you said and all the documents you knew about in real time. And so this is essentially the sort of the first idea of the World Wide Web. In 48, many of you probably know Claude Shannon for his amazing juggling machinery. But it turns out he also made some contributions to information theory. Actually, if you've never seen his juggling machinery, you should look it up. It's amazing. And he coined the term bit and basically invented information theory, on which a lot of information retrieval is based. Let's see, computer science degrees came along, the ASCII standard was developed. So we had an encoding of letters into numbers. The first email message, I believe that's the text of it right there, came along in 72. The various companies got founded, and by 1984, we had sort of roughly modern windowing interfaces to a computer. Third, the web has had a profound effect on information retrieval. In 1984, there were only 1,000 internet hosts. The World Wide Web was invented in 1989. And by 1992, there were 1 million internet hosts, but only 50 World Wide websites. Along came some graduate students who founded Yahoo, which was a manually built directory of the web. And by 1995, the Alta Vista engine was indexing 15 million pages, which was at the time was astounding. Google came along. By 1999, the Excite search engine sold for $6.7 billion. And this is last century money, right? So, and it was more than an actual car company that actually produced cars sold for it around the same time. By 2000, there were 1 billion public web pages, 3 million page index by 2002. And Bing came along, Alphabet market capitalization. I looked this up a few days ago. The market cap for Alphabet is over $2 trillion. So information retrieval is a big deal in the business world. But it's not the most recent change. The most recent fundamental change in information retrieval was the neural revolution. And this, you can trace this back maybe to 1943, when McCulloch and Pitts showed the Turing equivalence of a calculus based on neurons. That they never implemented that. That wasn't implemented until Rosenblatt invented the perceptron. And in 1969, Minsky and Papert put out a paper that said the perceptron cannot learn the XOR function. And even I said it wrong. A one-level perceptron cannot implement XOR. And everyone took that to mean that perceptrons couldn't do XOR, which is not true. A single layer perceptron can't do it, but if you stack the layers, it can. But this general perception of neural nets not being capable was one of the things that led to an AI winter around that time when funding for AI really dried up. But people kept plugging along, and backprop was popularized around 1985. In the mid-2000s, folks figured out how to use GPUs to train deep neural networks. The first real retrieval based on neural networks was, and I can never pronounce this, yeah, whatever, and Hinton, proposed semantic hashing, which was sort of like hashing, but the thing you're hashing on is not the string, but the concepts. And in 2017, attention is all you need came along, and I'm sure you've heard about that in the MT lecture, among others. And that really fundamentally changed basically everything. The Colbert system came along in 2020, which is a state-of-the-art neural retrieval system. And then the various GPTs came along and changed the way you had to think about using neural systems to do retrieval. All right. So that's the history. Any questions about the history? Okay. You are, by the way, welcome to ask a question at any time. Otherwise, you'll just hear me droning on. So part of what has been fundamental to modern information retrieval is the cost of storage. And so here we see a graph showing from 1957 that a megabyte cost $10,000. And the rapid decline in the price of space. At the same time as there's an increase in the amount of space you could put on a disk that looked like this. So these phenomena changed the way information retrieval was done, because at one point, way back when, you couldn't even store the dictionary of your words in main memory. That had to go on disk. Okay, but now you can basically store anything on disk. I was gonna ask, you probably saw it. What does a terabyte cost these days? All right, you saw it. Okay, you're too fast. Yeah, so you can get a terabyte for this. What do you think if you wanted a terabyte in 1957? What would it cost in? I guess did I do it in today's dollars? Yeah. What do you think? How many think it would cost more than $1 million? More than 10 million? More than 100 million? More than $1 billion? More than 10 billion? More than 100 billion? Okay, $10 trillion. The price of disk has come down. All right, so let's talk about the core concepts that we're going to use. Yes. Oh, yeah, I don't think you could have done it. You couldn't build it. It would be too big, I would think. In 57? Like
cassettes or something like that? Or
no, not cassettes. I don't know. That's actually a really interesting question. I don't know. Spinning platters didn't come along until the 60s, I think.
not be even technically possible to store so much data.
Well, you could, yeah. I mean, if you could have a megabyte, right? So if you could have a megabyte and you could replicate that, you could, but it's just it wouldn't. Newspaper, yeah. Huh? Paper tape, maybe, although the paper tape is hard to do random access on. So, but yeah, paper tape was a way that a bunch of stuff was stored. You punch holes in paper tape according to the ASCII codes. Pretty interesting. All right. We have several definitions to do. So document, this is the retrievable unit of text. Okay, so, and information retrieval always talks about the thing you're retrieving as a document, whether it's speech, whether it's a transcript of something, whether it's 1,000 chat messages, or it's a part of a document. Some people, especially in neural systems, now you have to chop documents up into segments. The thing you're retrieving, we're going to call a document. A whole bunch of documents is called your collection or your corpus. The plural of corpus is corpora. And so this is a set of documents to be searched, and we talk about the collection size as the number of documents in that collection. An indexing term, or also called just a term or a token, is some word, phrase, or lemma, or stem, or subword that you're using as the unit of expression for the meaning of the documents and the queries. Your dictionary is also called the lexicon, also called your vocabulary, is the set of word types, or yeah, we're going to call it, well, term types that you have. So if you're doing an English index, your dictionary is going to be a big set of English words. And the number of words in your retrieval system can be in the millions. So it's not, you're not going to have billions of terms, but you're going to have quite a few. A topic is a description of what the user wants to find. Okay, so it's an expression of their information need, and not necessarily in any form. We just talk about the topic as some sort of description of what they're looking for. And this is not the same as a query. A query is something you actually send to your retrieval engine, and there's a gap between information needs that users can express and what you have to put into the system. So we make that distinction. Some other core concepts. Oh, by the way, so this picture is core memory. This is how main memory was done back in the 60s. You had these ferromagnetic cores, and you had wires running through them, and you'd send a pulse through this way and pulse through this way and measure what happened, and that was 1 bit. And these were actually little rings that you could see. They were big enough for you to see them, and each one was a bit. So you can imagine you couldn't put too much of that together. Okay, a relevance judgment is an opinion about the degree to which a document is relevant to an information need. Okay, now this is a really weird concept for natural language processing folks, that it's an opinion, not a fact. And this is one of the things that has separated information retrieval from other natural language technologies. We'll talk more about that in a bit. Relevance judgments can either be binary. Yes, this document is relevant, or no, it's not. And a lot of the history of information retrieval has been done with binary judgments. But it can also be graded. So for example, you might say, this document is highly relevant. This one is somewhat relevant. This one is not relevant. We'll see a little more about that as well later on. Then there are a number of counts that we deal with. The document frequency is the number of documents in the collection that contain a particular term. So for example, the term "the" in an English document collection of 1 million documents, the document frequency for "the" is around 1 million, because almost every document is going to have the word "the" in it. On the other hand, the word kayak might be in only 10,000 documents. It might occur 18 times in every one of those documents, but the number, it's just the number of documents that's the document frequency. Collection frequency is the number of times the term occurs in the corpus. So this does take into account the number of times the term appears in any given document. And of course, the collection frequency of "the" in a 1 million document collection is going to be well more than 1 million, because most documents are going to have many uses of the word the. Term frequency is the number of times a term occurs in a specific document. Okay, so we might have document 5 that has 3 occurrences of the word people. So its term frequency is 3. Now, these are all absolute counts, right? This is counts of the number of occurrences of a word in some set. These can all be made relative, where you simply normalize by the total number of documents or the total number of tokens or the total number of tokens in the collection or tokens in the document. And so these are referred to as relative document frequency, relative collection frequency, or relative term frequency. People in the literature will abbreviate relative collection frequency to collection frequency. Okay, so when you see these terms, you have to pay attention. Is this normalized or not, right? Is this 0 to 1, or is this an absolute count? But this is how we're going to use it. Relative means normalized. And if it doesn't say relevant, it's not normalized. Questions about these, any of these definitions? Okay, so the first of our 3 pieces of information retrieval is, how do you deal with the language that's in the document or that's in the query? Tokenization is how we refer to chopping a document or a query up into the tokens, the bits that we're going to use for indexing. So here's a document that exhibits a number of issues for tokenization. There's 2020, and you might wonder, well, how am I going to index that? That might be indexed as the year 2020, right? You might have separate tokens for years, or it might just be indexed as the number 2020. Or for some systems, you might just want to know it's a number, right? So that's an issue. Mad Lib-esque. Anyone not know what a Mad Libs is? Okay, okay. Now, Mad Libs is a game where there's a text, but a bunch of words have been eliminated from it, like maybe nouns and adjectives have been eliminated. And people around the party say, okay, give me an adjective, give me a noun, and you fill them in the blanks, and then you read the story, and it's very funny, haha. Yeah. So, Mad Libs-esque. How many tokens is that? How many people think 1? 2? Okay, a few 2s. 3? A few 3s. 4? Okay. The answer is, it just depends on how you do it, right? It depends on what your purpose is and so on. It actually could be more if you're chopping it up into pieces. These are issues in tokenization, and there are lots of these issues that you have to figure out how you're going to deal with when you're tokenizing. One of the advantages of the recent neural approaches is that you have very few of these decisions to make, and we'll see about that in a bit. So if you are doing explicit tokenization, there are a number of tokenization steps that happen, and you need to know about these just in case you're reading the literature and you see these concepts. Obviously, case folding, mapping everything to, say, lowercase, is often done in many systems. It's not done as much in modern systems because there's enough data that has capitalization to be able to make distinctions. Back in the day, when there wasn't so much data, you didn't have, you couldn't distinguish, you didn't have enough training data on, say, the capitalized version of a word to get good statistics on it. Stop word removal is throwing away words that aren't going to help you. So most systems that use tokenized with English words will put the in the stop word list. It means anytime they see the word the, you just throw it away. Now, this doesn't really have much of an effect on the effectiveness of the system, but it does have a strong effect on the efficiency of the system, because you can imagine if you want to have you're building a concordance essentially, and you say the, you want to have a pointer to every document that contains the. That's a lot of space that's pretty much wasted. So stop word removal is often done, but it's mostly for efficiency. And then there's word form normalization. So stemming is a common one. Stemming is simply suffix removal. You build a system that chops off the ends of words. So you might have golfing, golfers, golfed. All of them, you chop off the end and transfer them all to golf. And that way, if you have some query about golf and there's a document about a golfer, you find it. An interesting fact about counting words is that words in natural languages typically follow Zipf's law. And Zipf's law says, one way of saying it is the kth most frequent term has frequency proportional to 1/k. Or another way to say it is that the product of the frequency and the rank is constant. So here's an example of one English collection that has been where we've counted all the words, and counting words is a big thing in information retrieval. We've counted all the words, and we see that if we put it on a log-log scale with frequency on the y-axis and rank on the x-axis, we get this pretty much a straight line. At the upper left is the very frequent words. At the lower right are the words that only occur once. And these are called hapex legomena. I've never known how to pronounce that. I've been teaching this for many years. No one's ever been able to tell me. It's probably, I could probably look it up. But anyway, that just means a word that occurs only once in your collection. Okay? And about half of the terms in your collection only appear once. So when we're talking about word frequency, from a retrieval perspective, not all frequencies are equal. So here we have again a plot of words in rank order against frequency of the words. This is not a log-log scale, so that's why it's not a straight line. But we see here over the left the most frequent words, like the, a, and, they're not very discriminative. That is, you want an indexing term to discriminate documents, discriminate the documents that are relevant from those that aren't, right? So if the is in every document, putting the in your query doesn't help at all because it's not going to distinguish some documents from others, right? So the very high frequency terms aren't discriminative. And so we don't really like them as indexing terms. At the same time, the rarest words can really only affect very few documents. So while they may be important for those few documents, in general, they don't affect the ranking of many documents. So we like to have the significant words from a retrieval perspective as the main terms we look at. And these occur in the middle of this range here. Questions on counting words? Okay, so we can count these things, but how do we find them? Well, first we have to segment the text. And there are at least three levels of segmentation you need to do. You need to figure out where the sentences are. Then you need to figure out where the words are. And then you might have to figure out where the parts of the words are. So we'll look briefly at these. Sentence boundary detection in English is actually pretty hard. In some languages it's not because there's like the Chinese full stop character is an unambiguous end of sentence marker. Periods in English are a big problem. Dr. Mulholland of Mulholland Drive says that in other languages, sentence segmentation is not so easy, et cetera. There are 6 periods here, only 2 sentences. Okay, so how do you know whether a period ends a sentence or not? That's a problem. And for something like machine translation really likes to have parallel sentences. Right? So if you're building this big parallel collection, you want the things on both sides to be sentences. So you want to be able to find where they are. And you can do that rule-based or through machine learning. Word boundary detection in some languages is pretty easy. So English makes it fairly easy because we have a space between words typically. In other languages like Chinese, all the characters get run together. So you don't know where the words are. And in fact, a lot of use is made out of that because you can embed ambiguities in your text that convey more information than just a single one best interpretation. Doing word boundary detection can be done rule-based or through machine learning, or you can just ignore the problem. And this is where we're going to end up. Morphological segmentation is breaking apart a single word into its morphological components. I'm not going to talk too much about that here. Let's say here's a Finnish example. And Finnish has a huge amount of morphology. And so you can have 100 different word forms for a single root. This is an example of an attempt to automatically segment this word, which means congressman, into its component parts. And there are a lot of different morphological processes that you need to deal with if you're doing morphology. Things like compounding, where in some languages like German, you can take two words that are good words, you can glue them together to form a new single word, perfectly legitimate German word. It's never been seen before, it will never be seen again, but it's a legitimate word. You just shove these two smaller words together. Okay. So to effectively retrieve based on German words, you have to have some sort of segmenter that will decompound the word. And so there are all these other kinds of morphology that you may have to deal with. And old-time systems spent a lot of time figuring out how to handle such morphology. One of the main ways, as I said, was stemming. It's applicable to alphabetic languages. It's an approximation to lemmatization. So lemmatization is finding the actual root of the word. Stemming just fakes that out by just chopping off the end. Most stemmers are rule-based. So here's an example of a very simple stemmer that maps juggling, juggles, and juggle to the same term. Now, there's a famous English stemmer called the Porter stemmer. It was a rule-based stemmer and became very popular. And it got so popular that everybody who wrote a rule-based system called their system a Porter stemmer, even though it was not the Porter rules. So Porter got frustrated and set up this snowball project where this is sort of Porter by Porter, and it has an English stemmer and stemmers for other European languages. So if you happen to need a stemmer for a European language, this is a reasonable place to go to get it. Okay, subword representations. This is how things are done now, typically. So with subwords, you're using pieces of words for indexing. So you're chopping the words up somehow. So let's say this is our text. Awesome sauce chillax and Fitspiration are recent portmanteaus. How are you going to index this? You can imagine that if this were a document, these terms are probably not going to be very frequent. They're fairly recent coinages. So we're going to break these terms up into pieces. And there are two main ways to do that. The old way is called character n-grams. And in character n-grams, you pick some n, like 5, and you chop your text up into overlapping sequences of 5 characters. Okay. So this is the start of the character 5-gram tokenization for this text. Blank AWES, AWESO, WESOM, and so on. Okay. So each character is appearing in more than one token, which has implications. But this is how subword tokenization was done for a long time. And it was really effective. There's really interesting history, which I don't have time to get into now, but if anybody wants to hear an amusing story about an article on Science that was controversial. You can talk to me later. So that's the old way. Byte pair encoding is the basis for the new way of doing things. And the idea behind byte pair encoding is that you're not doing overlapping pieces. You're breaking the words up into sensible pieces. For some definition of sensible. So here you can see that there's a byte pair encoding breakup of this text. And you can see the subwords are variable length, right? This is the way tokenization has been done, say, for the past 6 or 7 years, maybe. Subwords has some real advantages over other kinds of tokens. So they counteract data sparsity. So if you have, you're training on some collection, and you have very few occurrences of some term, or there's some word that's out of vocabulary, okay? It's just not in your collection. What do? If you're just using words, that term is lost as an indexing term, right? But if you can break it down into pieces in such a way that the pieces occur in the document, even though that particular way of putting them together does not, then you have a much more effective system because you're getting information about parts of the word, even though you don't have information about the whole word. Right? There are some disadvantages. The two main disadvantages are that they tend to build larger indexes because not every character begins a word, but every character begins a character engram. This is not so much true of the byte pair encoding, but the other thing is that they tend not to play well with word-based systems. So if you do everything in terms of pieces of words, and then you have some system over here that deals with words, a parser or something, you have to have some way to glue the pieces back together. And so that's an issue for these types of tokens. Here's just a comparison. This is just character engrams. And you see here a chart of, I believe this is a measure called mean average precision. Virtually every measure in information retrieval has the bigger the number, the better. Okay, this differs from like word error rate or something where you're trying to drive it down. If you're in information retrieval, you can almost always rely on the fact that the bigger the number is, the better the system is. Okay, so these graphs are showing this mean average precision performance over several different languages according to different tokenizations. So the very first one is just using words, break the words apart, you don't do anything to them. And you can see that performance is generally lower for all these languages. If you use some sort of stemming, performance gets a little better. But if you do character engram tokenization, you can see that for some languages, it doesn't really matter. English and Spanish, maybe do a little better, but not a lot. But for morphologically complex languages like Finnish, you get a huge benefit out of it because the pieces of words are capturing that morphology where you don't have any information about the word as a whole. So subwords are a really powerful way of tokenizing. So as I said, byte pair encoding is the technique that is used now, or the technique underlying what's used now. They put bells and whistles on it, but so this is how we do byte pair encoding. You start with some big training collection, okay, just some big wad of text. And then you take each character that's in that text and treat it as a single token. Okay, so you start with an inventory of a bunch of letters. Okay, here in our example here, our training collection is she sells seashells. And so we start with these 6 tokens. And what we're going to do is repeatedly find another token and add it to our inventory. Okay, so we do that by finding the most common adjacent pair of tokens. So here in our example, blank S is the most common character bigram in this text. So we take blank S and we add it as a single token to our inventory. And then we replace all the blank S's with this new token. Okay, so we have increased the size of our subword inventory, and we've shortened the training text a little bit. And we just repeat that, okay? So LL is the next most common one. We add LL as a token and replace all occurrences in the training text with LL. Yes. Oh, the question is, why does it choose LL, not EL? They occur the same number of times, so it's just random. Yeah. So the question is whether when you have a choice, is there a preference over putting together longer ones or more words or so on? And that is a decision that particular systems make decisions on. And it is an issue because you can end up here with multiple ways to tokenize a string, and so different subword segmenters will handle that issue differently. Okay, yeah. So the most common pair might include previously made tokens. So here, LL followed by S is the most common. So we make a new token LLS and replace all the LLSs with that token. Like so. Okay, so this is how it works. You keep doing this until you get a desired vocabulary size. Okay, so in this approach, you get to choose how many token types you have. And that's how you decide how to stop. So here are some examples. Yes.
So generally the algorithms are greedy.
Yes.
Is there some global optimal algorithm that would like choose all the possible combinations and pick the best one?
Well, so I don't think there's any one. Let me just point here and then I'll talk about that. So there are sort of two main flavors that are used these days often, word piece and sentence piece. And they handle these questions differently. Okay, so for example, in word piece, you have to segment the words first. Okay, so you have to have a word segmentation. You do that step before you do the tokenization. That means that it works fine on English, maybe not so well on Chinese, because you don't know where the word boundaries are. In contrast, sentence piece doesn't require you to find the word boundaries. Okay, so decisions like that are going to control what it means to be the best breakdown. Okay, and the sentence piece actually does a bunch of other stuff to try to have a unique tokenization and to make sure you're getting efficient breakup of the word. So there's an alternative version that starts with all the possible terms and then whittles them down. Okay, that is used too, and there's a part of sentence piece I think that does that. But the details get complex, as you can imagine, because there's a lot of phenomena you have to deal with.
Because I'm from Vision and I read papers that use PPE. So first of all, is there like consensus on this? Like, let's say there's one tokenization that's already been done on a few people or something like that, or everybody?
Yes, there is. So the question is there a consensus on how to do this? The answer is yes. Word piece and sentence piece. Okay. So, and it's important because to jump ahead, BERT is a particular language model that uses this word piece tokenization. Okay. If you are going to use BERT, you must use that tokenization. Okay. You can't say, oh, I like this tokenization better, I'm going to use that, because then it's not going to align with the language model. Okay, so you have to use the tokenization of the original language model. So really, that means you have no flexibility, because the language models that are out there, you're not going to create a new one, right?
So in Vision we have this same. We have foundation or backbone models that are pre-trained on some large corpus, So, and everyone is using the same weights. So I can imagine the same is going on with the BP. Like everyone is using the same, you know?
Yeah.
Sorry?
In machine translation, you have some training data, so you train the vocabulary of the data using the algorithm.
You do.
Yeah, very fast.
But then you created your own tokenization that you can use only with your model, and you have to distribute it with the model. But I imagine like
Right, but for machine translation, for those online, the questions are about parallels between essentially the equivalent of tokenization in vision and in machine translation. And in machine translation, you can make up your own tokenization because you're really only caring about the parallel sentences. You're typically not going through, not piping through an existing language model, right? Whereas I think in vision, it sounds like you cannot, you have to use what everyone else has used. Is that right?
well, you can, but you know, they make it hard for you. So I imagine it's the same word. Yeah, I don't know. I will use just the tokenization that was pre-trained on some data set.
Yes.
I will just use it, not
That's, yeah, you just have to use the BERT tokenization because it's the only thing, it's the only entry into BERT is through these tokens. Right.
Otherwise, I would need to train the word from scratch on my data. Let's say.
Yes, I mean, you could do that if you want. You can train your own. And back a few years ago, people did that, but okay, somebody remind me when our break is and then we'll get to, what was it, break is when? 10:20, okay, great. Questions?
Maybe I'm also have the frequencies of the individual tokens, right? So do I do it greedily, just
Yeah, okay. So yeah, the question is, you've got these tokens. How do you now tokenize a new thing? And you use the software that that they used, but you know, it's a lot like you typically don't do this yourself, right? If you were building your own model, then you would have to decide how to do that, right? But since you're probably not going to build your own model, you don't get to decide.
You have like a large vocabulary set. I think a reason why you do tokenization on the spot in machine translation is not small vocabulary set, which is a very important parameter. Meanwhile, if you do on Bird, you just have like you come from a large vocabulary set. If you train your phone on it, you have like a zero small vocabulary set.
Well, so the question is about vocabulary size and machine translation versus BERT. This slide shows the actual size of the vocabulary. And remember, you get to decide how big your vocabulary is going to be with BPE, right? So all the systems have done about on the order of tens of thousands of terms for English, monolingual English work. If you're doing multilingual work, you have to have a larger vocabulary because otherwise you'll just essentially get the Unicode set as your as your tokens, right? Yeah, and in the back, and then you.
But there's ongoing papers about how to remove the tokenizer and to swap it with the different one. And basically, like the idea is to find a new neural network to learn the embeddings of the model. And which is great because like one of the issues of the tokenizer, as you explained, is that you train your model on English, your tokenizer on English, and now you want to use it for, let's say, Indian languages, then you will have issues with the length of the sequences. And so, yeah, currently like a lot of paper trying to really solve this problem, tokenizer issue.
Yeah, so the comment was that there is current research on how to take an existing tokenization approach and do the tokenization differently and update your model to reflect the new tokens, okay? So yes, there is that work. That's fairly recent and it's not universally used, right? And so for the most part, if you're gonna come in and you're probably gonna use some existing model like BERT And so you're going to be stuck with that. Question?
In the word piece, I prohibit characters on the boundary between words from becoming a single token.
So the question is, what are the differences between word piece and sentence piece?
Cluster the characters tokens when doing on the word separately when you do it on the purpose.
Oh, so for you're saying for word piece in particular.
The algorithm is not giving the whole timing purpose. But it seems that for word piece, I sort of split up the timing purpose into lots of tiny corpora where each one is specific
Yeah.
word, then I
Yeah. So the comment is that for word piece, you have to split your whole corpus up into a bunch of words first. And that's true. Why would you want to do that? You would want to do that because you want to use bird. Okay. That's the reason. Okay. There's not a lot, there's no fundamental reasoning behind these things. It's just that's what was done. Okay. And sentence piece tried to correct the fact that word piece is proprietary, that it word piece required word segmentation, and it also addressed this subword regularization thing where you were sure to get the same tokenization even if there's some ambiguity. Okay, so those are the main differences.
let's say in the gardener in the market, right? These two words appear so frequently together, so I guess there is a single token for those. Whereas in word piece there is no such token.
Yeah, so the question is, if you had the sequence in the, word piece is going to not have that together as a token. Sentence piece is going to have a single token for in the, yes. Okay. All right, so these are monolingual English dictionary size counts. Multilingual, as I said, you have to have more tokens. All right. Okay, so we've talked about a bunch of this. Word boundaries, blah, blah, blah. All right, yeah, so we talked about all of this. The word piece doesn't use BPE's approach of just taking the most common adjacent pair. It actually picks the pair that maximizes the likelihood of your training data if you have a new language model based on that tokenization. Okay, so it's theoretically a little better, but you know the idea is generally the same. Word piece does have these special tokens, CLS token that comes at the beginning of the input, SEP token that to separate the pieces like sentences. So there's an example there. And people will use, if you want to have a single vector to represent your entire sentence, people will use the vector that was that the CLS token was trained to. Okay, so this is useful if there are too many, if the size of your data is too big to handle one vector per token, you can do one vector per sentence that way. Let's see. Oh yeah, and for this is a general notion of how do you map back from subwords to words. And basically, these things are all taking tokens and mapping them to some vector. And so if you have a word that's broken up into two pieces, you have two vectors, how do you handle that? Some folks will just average those vectors. Some will just use the first one or the last one, and so on. Okay, that's word piece. Sentence piece is open source, doesn't require segmentation. It's available. There's an example. Okay. Anything else on tokenization? Yeah.
Most of the models models share similar vocabulary size except for birds. Like most lingo is like significantly smaller than the other two. Is that a reason? Is that particularly because of word keys or any other choices that occur?
I don't know the answer to that, but my guess is that it came first, and you couldn't do that big a token space. That'd be my guess. That as time went by, you could afford to have bigger and bigger dictionary sizes. Okay, so we have these tokens. We want to have a way to assign meaning to these tokens, right? So we're going to use vector representations. And in 1957, this paper came out by Osgood, Suchi, and Tannenbaum, and they had nothing to do with information retrieval. They were trying to come up with a way to describe the meaning of different words. And they came up with 3 dimensions: valence, arousal, and dominance. Valence is like good or bad. Arousal is how strong the word feeling is, say. And dominance, I've never understood what dominance meant. I've looked several times. I couldn't figure out. But it doesn't matter. The point is that they took a bunch of words and assigned values in each of these different categories. And so if you look at the rows here, essentially every row is a vector, and that vector captures some aspect of the meaning of that word. Okay, so this is the essential idea behind how we're going to represent word meanings. So there's heartbreak. Valence is low. I think these were 0 to 10 scale. So heartbreak is a bad emotion, low, so it has low valence. And arousal, it's sort of medium intensity, and I don't know what dominance is. So that's the idea behind vector representations. And there's been a whole series of approaches to doing this. This is a term document matrix. So we have on the essentially the y-axis the set of tokens in our vocabulary, and along the x-axis are the various documents in our collection. So we see that each row, each column represents a document. Okay, and so here's document 5 has the word cats and the word lives in it. Okay, and so we can capture sort of the meaning of a document this way, but we can also use it to capture the meaning of a word. Okay, and the meaning of the word here is simply the set of documents that contain that word. Treat each document as a separate dimension, and so you get a vector of that where the ones represent documents that have the term and the zeros don't. This is what's called a sparse vector, typically because you have a lot of zeros. All these early systems had a lot of zeros in the vectors, so we call them sparse. So this is our vector representation for cats. Here's a sparse vector example. So let's say we've selected just 5 terms for our tokens. Document 1 has, would you like a cup of coffee? And our 5 terms are coffee, tea, milk, sugar, and cup. So the vector for document 1 would be 10001 because it has coffee and its cup, but not the other words. Okay. When we look down at document 3, the recipe uses a cup of milk and a cup of sugar. Here, cup occurs twice, so we count it twice in our vector. Okay. So you can see how these would be sparse because if the various dimensions are the words in your vocabulary, the tokens in your vocabulary, and your vocabulary has 30,000 or a million or whatever words, a sentence is not going to have that many. There are going to be very few ones in that vector. Okay, so it's a really sparse representation. So one thing people wanted to do was reduce the size of the representation. So here we're looking at a word matrix, which is the number of times a given word appears, say, within 2 words of another word. So the first one there on the cats row says that cats and radioactive occurs once within 2 words of cats and radioactive occur once within 2 words of each other in the collection. Okay. So we now have a word matrix. This is also a perfectly reasonable representation. But we'd like to reduce the size. And we're going to use what's called principal components analysis, which is basically you have a big vector space. You find the dimension that has the most variance. Okay, that's the first principal component arrow here. So that's the dimension of these data that has the most variance, and you make that your first dimension, and then you find the next most variance, and you order the dimensions along that line, and then you just do a linear transform of the space according to those new dimensions. Okay, so folks use this to produce dense vectors using a technique called latent semantic analysis. And here's the idea. We're going to use the term document matrix. We're going to decompose it into 3 matrices, the middle one of which is a diagonal matrix. And when you multiply them together, you get a matrix of the same size as the original. And you sort these according to the principal component analysis. So in the upper left of the diagonal matrix there is the most important dimension. And the lower right, see if I have a pointer here, like this. Laser pointer. So up here, this is the most, the dimension that's most important, has the most variance. And down here is the dimension that has the least. And what we're going to do is we're going to just cut these matrices up, right? So we cut them up so we keep the shaded area for each one. And then we just save those and we throw the rest away. But the nice thing about this is that when we multiply these together, we're still going to get a matrix of the same size. And it's going to be almost the same as the original matrix. Because we've only thrown away the dimensions that have the lowest variance, right? So we can reduce the size of our vector space using this technique. And so this was the latent semantic analysis and latent semantic indexing, sort of the indexing form of that. Was an early attempt in the late 80s to shrink the vector space and move towards denser vectors. It never really caught on. It didn't really work all that well, in part because back then there weren't these huge collections of data that could identify the nuances and so on. But it was an early way of doing that. And the next approach was what's called static embeddings. So with static embeddings, you're going to have a vector for each token, but you're only going to ever have one vector for any given token. Okay, Word2Vec was the first popular one of these, and Word2Vec worked by trying to train a system to have it would pick a word, and then as a positive example, it would pick a word within say 2 words of it, and negative examples would be some other word. So here, apricot occurs near tablespoon in this collection here, but it does not occur near aardvark or 12. So here we have a couple of training examples of, for apricot, what's a related word and what's not a related word. And Word2Vec used this in a basic architecture that looks like this. Here we have an input layer, and this is a what's called a one-hot vector. This has one dimension for every word, and there's a single one in it for the word that you're talking about, and all the rest are 0. Okay? And it went through these 2 matrices to produce an output that was just a probability distribution over the words that would occur near the input word, using those training examples. Okay. And yes.
So when you say word here, do you mean really a word or
Okay. When I say word, I mean token. Yeah.
Okay.
Whenever I say, unless I clarify, whenever I say word, I mean token. because that's, IR folks tend to just talk about words. But yes, so these are going to be subwords in reality. But the interesting thing is you train up this thing to try to predict what words are going to be around it, and then you just throw everything away except this W matrix. And you just keep the W matrix. And here, the original way you thought of this is a bunch of neurons. Say you wanted 300 dimensions. So you have a bunch of neurons with 10,000 words each. Say that's for your vocabulary size. If you look at the rows, you essentially have a mapping from words to vectors, right? So you have, for every word, you have a 300-dimensional vector that represents it. And it captures a lot of that information about what words occur close to each other. That's the way word2vec worked. And so you got these static embeddings where the word bank only had one embedding, and the money bank and the river bank had to sort of coalesce at that point in your vector space. So it was good, but it had this problem that it wasn't contextualized. Just to give you an example of dense vectors, here's an example of a 50-dimensional word2vec where the different colors represent the different weights of the dimension. And you can see that there's some regularities across these. This A column almost looks like it has some meaning, right? What would you guess the meaning for the A column would be? Pardon me? Person. Okay, yeah, that's perfectly reasonable. It could be person, it could be animate, or we don't know. And in fact, it doesn't actually mean any of those. It just means this is how the vector space worked out, right? But we do see that it is capturing some of the semantics of the words. What about the B column, the B dimension? What do you think that would be?
Like constant.
Like what?
Like constant.
Constant?
B.
Yeah, so that's a good guess. This might be a noun. We don't have any verbs in this list, so we don't know. But you can easily imagine that would be reflective of nouns, right? What about C?
Like age,
maybe? Age. So child, something like that. Yeah, anyway, you can look at these vectors and see how they capture some of the meaning of the words, right? And you can believe that they do that. The common thing that people did here was analogies. The most famous one was king minus man plus woman is about equal to queen. And here we have in the same representation, the vector for king, man, and woman. And the fourth one there is if you take the king vector, subtract the man vector, add the woman vector, you get that. And the vector for queen is at the bottom, right? And you can see they're pretty close. That's not exact, but they are pretty close. If you look to see how close they were, they'd probably be pretty big. Okay. There are other useful static vectors. If you're going to end up using static vectors, you probably want to use one of those, but and I'm going to rush through a bunch of stuff here because we're low on time. Transformers, I'm sure you heard about those in the machine translation. Transformers changed everything, including information retrieval. For example, BERT used transformers, and it had a masked language model. So it would mask out words in the input and try to predict them. So here, if the input had a mask on the penultimate token here, it would give you a probability distribution over tokens that said how likely those tokens were to fit that spot. There are other contextual models you all know about. Okay, good. So we want to now put these all together to form a representation of an entire document or an entire query. Bag of words was always the traditional way to do this. So you take your text and you throw all the words in a bag, and then you can count all the words in the bag. And so you can see that, for example, hello occurs 5 times. And you would use these statistics to build your system around. We talked earlier about counting, and counting was very important for building these systems. We can do bag of vectors, and in bag of vectors, you basically do the same thing, but you throw all the vectors for the tokens in a big bag. But then you can't really count them because if they're contextual vectors, they're all different, right? So you have to use something like an approximate nearest neighbor index, which is a system that, given one vector, tells you what the vectors near it are. And face is a commonly used one put out by Facebook. So we use that icon there. Okay, we are so far behind. And we're almost ready for break. Why don't we break now and then come back at 10:30? Okay, we'll break down and come back at 10:30. And if you have questions, you can then ask me. Okay, why don't we get started again?
10 more minutes.
10, oh, we have to do 10 more?
Official schedule.
Yeah. I thought I had changed that now.
Oh,
Oh, we'll give a couple more minutes, but we stopped a little early, so I didn't want to lose that time. Um, the questions are great. They really are. This is like the most questions I've ever had, and it's really fun. But they have slowed us down. So we're not going to get through all this material. And I'm going to fly through some of it that is perhaps less important. I doubt we'll get to cross-language retrieval at all, but I do want to get to evaluation because it's such a big part of the IR research community. Okay, so we now know how to represent documents, right? We have a bag of vectors. And now we need to be able to say, oh, here's a document, here's a query representation. How close are they? Is this document relevant to this query or not? So the old way of doing things was a Boolean model. You put together ands and ors and nots, and you have a query like strawberry and pie or tart and not meringue. And if a document met that criterion, you put it in the return set, and if it didn't, you didn't. And it was very easy for people to understand why a document was returned, because you either had those terms in it or didn't. We're going to skip this. Boolean queries are useful. They can have very good performance, but the terms aren't weighted. There's no penalty. If you have a lot of terms that don't match the query, the results aren't ranked. They're hard to construct. So imagine trying to have a Boolean query to find weapons. You can have, knife or gun or hammer or sword or bow and arrow or rope or et cetera, right? It would be a very complex query for a simple concept. So Boolean queries is where information retrieval started back in the 50s. But we want to have weights on our terms. We'd like to know which terms are important and which ones aren't. So, if our query is the juggler, we want more weight on juggler than da. Right? So we use a few concepts for this, typically. Inverse document frequency. So remember, the document frequency is the number of documents that contain a term. They might contain it once or many times or so on, but it's the number of documents that contain the term. Relative document frequency is normalized by the total number of documents, right? So relative document frequency is just the percentage of documents that contain the term. And as we talked about before, the medium document frequency terms are best for information retrieval because the very common ones don't distinguish documents and the very rare ones don't affect many queries. And so we use the concept of inverse document frequency. And inverse document frequency is simply the log of the inverse of the relative document frequency. Okay. And this is a very common way of helping to weight terms. So the effect of IDF is if you have a term that appears in every document, your IDF is going to be 0. Okay. If you have a term that occurs in only one document, the IDF is going to be very high, right? And in general, we want bigger IDFs. As the bigger the IDF, the better the search term, except when you get down to the very tail there. The most common way this is used is what's called TF-IDF. And if you look at anywhere in the information retrieval literature, you will see this term TF-IDF. This simply means the product of the term frequency and the inverse document frequency. So the term frequency, remember, is the number of occurrences of a term in the document. And the IDF is what we just talked about. So there's the formula. Term frequency is going to be relative term frequency. Document frequency is relative document frequency. And you just multiply the term frequency by the inverse document frequency. Okay. And this is a weight for a term in a document. Okay. So you're trying to represent this document. The word juggler occurs in there. You're going to weight it by the number of times it appears in the document and sort of the inverse of how frequently the term juggler appears in the whole collection. Okay. So that's how we assign importance to terms. I say that this is a very common way to do that. You will see it written as slash, minus, times, nothing. They all mean the same thing. Okay, there's no division or subtraction or multiplication here. Well, there is multiplication, but they all mean the same thing: term frequency times inverse document frequency. If we have now vectors that are weighted in this way, we will want to judge the similarity of two different vectors. So if we, for example, have a single vector representing the whole document, if we do, I mean, there are different ways to do it, and a single vector representing the query, we'd like to see how close those vectors are, and we can just use the dot product. And the higher the dot product, the closer the vectors are. So in this example, document 2 has the highest dot product score with our query, so we judge that to be the most relevant. Okay. So we use dot product. Of course, we can normalize by the vector length, and if we do that, then normalized dot product is just cosine. And so you will often see cosine retrieval, the word cosine used to talk about a method of retrieval. And that simply means we're taking the cosine of the angle between the query vector and the document vector. And the closer those are, the higher the cosine. Right? TF-IDF, a very commonly seen term, cosine, very commonly seen term. And cosine is how you're telling whether two vectors are similar. A third similarity metric is called a CAPI-BM25. And this is a similarity metric that takes into account both the importance of the document term frequency and it normalizes for the length of the document. So if you have longer documents that match the same number of terms, it's probably not as good as a shorter document because the shorter document is going to be more focused on your topic. So there is in the lower right here a penalty for document length. BM25 is probably, well, I don't know, probably the most used commercial approach. It's the folks who did it basically did a large search over space of weightings in this formula. There are two parameters, and K1 and where's the other one? K2, I don't know, somewhere in there. And they found the best values for it, and people have been using that for 30 years, right? And then they just plug it into this formula. So BM25 is another similarity metric. How do you compare two vectors? Now, there are similarity metrics that are based on language models. So we'll talk about unigram language models. A unigram language model is simply, well, a language model is just any model that generates text. And a unigram language model is basically generating all the words individually. They're just treating words as separate components and not worrying about how they go together. We can take a document and turn it into a unigram language model, right? The document has a term frequency for each of the terms, and we can build a language model that just generates terms with those frequencies, right? And this assumes term independence, which obviously words are not independent. And we don't care because it's never seemed to matter that the words were related to one another when we're using these sort of this bag of words way of thinking. If you do this, you're going to want to calculate log space because otherwise you'll get underflow. Now, if we take this language model based on the document and there's some query that has the word juggler in it, and the document doesn't have the word juggler in it, then that language model is going to say, oh, that's the probability of juggler is 0. Right? So we don't want that. So we want to smooth the model, and there are a variety of ways to do that. Jelinek-Mercer smoothing is a common way where you simply average the probability from the language model based on the document with the probability of the term on a language model based on the entire collection. Okay, and you just take a linear combination of those. So here in the lower right, we have alpha times the term frequency, the normalized by the length of the document. So this is the relative term frequency. And 1 minus alpha times the collection frequency. Okay, so it's a very simple language model, but it turned out to be very effective, probably more effective than the previous models. These came around the turn of the millennium. There were 3 main ones at the beginning, and they just often outperform vector approaches. So it's a very simple similarity metric, and it's very effective in a statistical system. So to use this unigram language model for similarity, we're calculating the probability that each language model would produce the query. Okay, so there are other ways to do it, but this is probably the most common. You take the document language model, and you have a query over here, and you're saying, well, what's the likelihood that this model would have generated that query if we just generated text at random from the model? Okay, so and what we see here is just taking the probability of each query term being generated using that smooth model, and we just multiply those probabilities together, right? And that's the probability that document produced that query. Okay. Again, it assumes term independence, but we don't care. And we just take that score as a measure of similarity, and we order them according to that score. So the ones with the highest score, those are the most where the document is most likely to generate the query, and we say that's the most relevant. Okay, so that's another similarity metric. There was a lot of scuffle back in the day over what the best value of alpha was. Just use 0.5. You know, if you're going to do this, just use 0.5. It works fine. You know, you might use a point of performance, but it's not worth it. Here's an example that is way over-engineered, and I'm not going to do it. Okay. So we're sort of, we're up through most of the non-machine learning based retrieval systems. Okay. Now, one thing we might want to do is expand our query. So we have this query. It's got a bunch of terms in it, but there are terms that we didn't think of. You know, we wanted a query about trucks, but we didn't think to add the word lorry. And so what we'd like to do is take our query and expand it in some way so that it does contain lorry. Now, how are we going to do that? There are basically two ways to do it. You can take some thesaurus and just say, look, you look up truck in the thesaurus and it says, oh, another word for thesaurus is lorry. You can add that back into the query and run the query again. So these are all two-stage models, right? You run the query, you get information. Oh, no, I'm sorry. That's not. You can do that right away with that before you run the query. The second one, the relevance feedback, you can't. So relevance feedback is where you take documents that the user has judged to be relevant. So you do a retrieval, you give them some documents, and they say, oh, that document is relevant, but that one is not. And they say, oh, that's a relevant document. Let me look and see what words are in there. Maybe I can add some of those to the query. So you do that. And I think we have, yeah, so for thesaurus expansion, you could do it. Doing it automatically can be risky because of polysemy and so on. So if thesaurus expansion is used, you often put the possible expansion terms in front of the user and ask them which ones they want to add. Relevance feedback, you have to get judgments on the documents. Okay? So you ask the user which documents are relevant, and then you either add terms or reweight the existing terms using the information from those relevant documents. So this requires manual judgment. So it does require two phases, right? You have to do the search, then modify the query, then do the search again. And you have to have a user in the middle. And there are two kinds of IR researchers, those who believe in users and those who do not. Mostly the folks who don't believe in users because it's inconvenient for them to think about users. So what you can do is what's called automated relevance feedback, or it's also called blind relevance feedback or pseudo relevance feedback. You'll see all three terms in the literature. And what you're doing here is you sort of abstract away the user and say, oh, I do a retrieval. Oh, these top documents, they must be relevant. Let's pretend they're relevant and do relevance feedback. Okay. So this is, again, a two-phase thing where you're doing the query twice, but you don't have a pesky user in the middle slowing things down. So typically you'll take the top K documents, pretend they're relevant. Possibly you'll take some of the documents as not relevant, maybe not. Yeah, so there are really two main formulas that people use for relevance feedback. Rokio is the older one. And basically in Rokio, you find the centroid of the vectors for the relevant documents and add that into your query. You can also subtract off the centroids of non-relevant documents. You can pretend that, oh, documents 100 through 1,000 are not relevant and add that in. For the most part, people don't do that. They don't add the negative terms back into the query because it's hard to know which terms are important to add in. Usually just adding in negative terms doesn't really help. So mostly Rokio uses the centroid of the relevant documents. The other is called RM3. And in RM3, it's a language model approach. you imagine all your possible language models from the documents, and you sum over them. And for each one, you calculate the probability that the word would have been generated by that language model. There's a prior in the language model, but I think that's usually just taken as uniform. And then you multiply it by the probability of the language model generating the query. You do so that was actually the RM1 formula. And so you take that, and that gives you a probability distribution over terms to add to the query. And then you just do a linear combination of that with your original query. And that's called RM3. That is also pretty widely used. But for neural systems, we need a different approach. And so we've already seen how you could use, say, cosine if you have two vectors, one representing the document and one representing the query. And you could use cosine as the measure of similarity, right? So that's if you have one vector for each. And that's a reasonable approach, right? Having one vector per document. But it turns out to be more effective to have one vector per term. And so if you have a document that has a whole bunch of terms and a query that has a whole bunch of terms, you need some way to do similarity across sets of vectors, right? So the main way that's done is called maxim. And imagine we have embedded our query terms here. And so these pinkish reddish ones are query terms in our embedding space. And here's our document. So we have a document in green with the black circles around them. And maxim basically just says, oh, for each query term, what is the closest document term to that query term? Okay, so for each query term, you find the one closest vector in the document. Okay? And then you sum those up, and the lower the sum, the better the similarity. Okay? So this is called maxim, and it's a way to take a bag of vectors and a bag of vectors and calculate a similarity between them. Okay? And the reason we start from the queries and look around for the documents is this. In almost all cases for retrieval, the query is much shorter than the document. Okay? That's not uniformly true, but in almost all cases it is. And everybody assumes the query is going to be shorter than the document. Okay? So that's maxim, and we'll see in a minute where that maxim is actually used. Any questions on this bag of vector comparison? Because we're going to use it again. Yeah. We can also use generative models to do similarity. So we can say, hey, GPT-4, how similar are these documents? The way this is sometimes done is you ask whether this document is relevant to this query. You can do that. You say, here's my query and here's my document. Give me yes or no, is that relevant? And you get a yes, oh, it's relevant. But it's not a number, right? And it's hard to use. So people will take the outputs and do and combine them in some way, usually softmax, and get a distribution over the terms. And then you look at the probability for yes and the probability for no. And that tells you whether the document is relevant or not. There we go, 0.52. This is a pointwise score. So this is a score assigned to each document. That's useful in some systems. Sometimes you want pairwise scores where you want to score for two documents. Is this one more better than this one, or is that one better? Sometimes you want to look at a whole bunch of documents at once. But this gives you a pointwise score. And it is a way to use a generative model to score the similarity of a document and a query. Okay, so that's our whirlwind tour of similarity, how we compare two representations. So before we go on, questions on that? Yep.
What you're softmaxing over is like the final activation?
Yes. Yeah, yeah, this is, you have to have access to the final activation levels. That's what you're using. Yeah, thanks. All right. By the way, this is very expensive. Nobody uses it except, nobody uses it in practice, you know, use it in an evaluation when you're trying to beat everybody else. Okay. Storing and processing IR data. So now we know how we're going to represent documents and represent queries and how we're going to tell how similar they are. But we need this infrastructure around them to be able to do it efficiently. Text retrieval has 3 stages: training, indexing, and retrieval. Okay. At training time, you are typically taking a pre-trained model and fine-tuning it for the retrieval task. That's usually how that works. You could do it from scratch, but usually you're taking an existing model. And you have training examples. And training examples are something to say, oh, here's a query, and here's a relevant document, and here's a non-relevant document. Okay? And you use those training examples to modify your pre-trained model in some way. You can fine-tune it or do an adapter or different ways to do it. So that's training. That builds a retrieval model. Okay. Once the retrieval model is built, you have to index your documents. Okay, so you have perhaps not seen your documents yet. And so you have to index them all, that is, build a representation of each document and put it into an index. And so this index is something that has to be efficient to find documents from, and you know, you're going to have document collections that are going to be very large, right? So there's a real efficiency issue here. There's also an efficiency issue in that in most cases you need reasonable response time, right? Like if this is a web search, you know, you do a web search and you don't have an answer in 2 seconds, you know, you move on to the next engine or whatever. So response time is very important. And so your index has to be able to find stuff very quickly. So at retrieval time, you take a query, you use the index to look it up, and you come up with a ranked list. Okay, so these are the 3 main steps in any kind of retrieval, mostly machine learning oriented, but even the old stuff have this. And so we're going to talk about these 3 phases for the systems we talk about. We're going to talk about these 3 phases: training, indexing, and retrieval. There is the notion that you want to be able to use very expensive methods, but you can't use expensive methods on a huge collection. So there's this idea of retrieve and re-rank. So you do a retrieval using an inexpensive system, you get back maybe the top 1,000 documents, and then you use your expensive system to re-rank those documents to give better scores to each of them, so you get a better ordering. And your hope is that in that top 1,000 documents, you have found most of the relevant documents, that your recall is high. So the first stage is a more efficient but less effective method that generates a high recall list. That is, most of the relevant documents you hope are in that list. And then you use a more efficient system to re-rank those. So this is an important technique that essentially uses 2 underlying techniques, but it's an important way to use an expensive approach and still have reasonable response time. Okay. Sparse information retrieval is the old style of statistical retrieval with sparse vectors. I'm going to fly through this. At training time, you do almost nothing. Okay, like for BM25 similarity metric, at some point somebody essentially trained that system. They looked at these 2 parameters and found the best combination, and that was your training, right? But for the most part, you don't do much training on sparse retrieval. At indexing time, you take your documents, break them down into terms, and you essentially build a concordance, right? You build a concordance where each word is mapped to the documents that contain that word. So here's document 684, and you can see that the words called chestnut 4 and feet all say that document 664 has them in it. And something like dormouse, that document is not there because that word is not in the document. Okay, so this is essentially a concordance. This index is called an inverted index, and it's the fundamental data structure for all pre-neural retrieval systems. These indexes are extremely efficient, right? People have had 40 years to make them fast. And so inverted indexes are still used everywhere. At retrieval time then, you take your query, you look at break it into tokens, you look those tokens up in this inverted index. Each one of these rows is called a postings list. A postings list is simply a map from a word to the documents that contain it. So you look up the postings list for those words, and then you run it through some similarity metric like BM25, for example, and you get back a ranked list. So that's the old inverted index sparse retrieval approach to information retrieval. The inverted index, we talked a little bit about this. Essentially, it's a concordance, right? But it's a very efficient concordance that can handle a lot of data. So this is an example of an inverted index. We have, let's see, do I have still this pointer here? Yeah. So we have 4 documents in this collection, okay? And we're just going to use words as the indexing terms. So for each, we go through, for each word, we say, oh, look, every is in document 1. Good is in document 1. Banana is document 1. So we record all these. There's one occurrence of each of these words in document 1. And then we go to document 2. All cows eat all grass. So we just basically counting for each term which documents have it and how many times they do it. And we use that to build this inverted index, which has 2 pieces. Our dictionary, which lists all of our indexing terms, and gives document frequency, that is the number of documents that contain it. And it gives an offset into this, what's called posting list, or the inverted file, that tells you where to look in this big index of terms. So if we want to find the word fudge, we look up fudge is in our dictionary, and it says, oh, fudge is in 3 different documents, and it starts at offset 22. Okay, so here these are 10, so that's 0, 10, 20, 21, 22. So fudge starts here, and there are 3 documents that contain it, according to the dictionary. So we see here that document 1 has 1 occurrence, document 3 has 1 occurrence, and document 4 has 1 occurrence. Okay, so this is how we find out for a given document. This is how we find that document when we know what words we're looking for in the document. Okay, questions on this? I can't tell whether this means, oh my God, this is so simple, you're boring me, or I have no idea what you're talking about. You might want to volunteer an answer to that. All right. I'll assume that this is fairly straightforward. This is just the primary data structure for most retrieval up until very recently. There is before the neural approaches, there is an approach that's called learning to rank. And basically, you're using machine learning to predict rank order, right? And this is widely used in web search. They'll use the learning to rank approach, often as a re-ranker. So you have an inexpensive retrieval system. You take the top documents and use your learning to rank system to re-rank those documents. And these re-rankers can use lots and lots of different features, both of the query and the document, and also the what you know about the user and so on. Okay, so this is a machine learning approach, and there are 3 variants. Point-wise, pairwise, and list-wise. In point-wise learning to rank, you're trying to learn how to score a given document against the query. And remember back we saw the point-wise, one of those approaches to a point-wise score. And typically you'll just use regression for this. So you'll have a bunch of training examples and you'll use regression to find a mapping. You can't exploit the fact that you know that this document is better than this one in the system because it's all single document scores. Okay? Second-wise, pairwise, you're trying to classify the relative relevance of two different documents. Okay, so you want the system to say, oh, this document, of these two documents, this one's more important than this one's more relevant than this one. Okay, and so you build a classifier for that that just says this is more important or it's not more important. It doesn't distinguish small differences from large ones, right? So if your query is about juggling and this document is about Sergei Ignatov, the great Russian juggler, and this document is about food processing in Thailand, it says, it may say this one is more important than this one, but it will also say that the one about Sergei Ignatov is perhaps more relevant than something about amateur jugglers or some other juggling related document. So this pairwise approach doesn't give you access to sort of how relevant the document is. And it's also sensitive to noisy labels. The third way is listwise, where you take a whole sequence and you try to learn how to order those. And there are approaches to that, but it's complicated and it's not all that widely used. Okay. But this is the learning to rank approach, and that's probably been the dominant approach for web search for, well, for 10 or so years until neural approaches came along. Okay. All right, so let's go to dense retrieval, right? We're trying to train a neural system. Dense retrieval just means retrieval over dense vectors. And to train a dense retrieval system, we need training examples. And these training examples are you have a query, and you have a document that's relevant to that query, and you have a document that's not relevant to that query. And you have a whole bunch of these, and you train your system off of them. For example, there's a collection called MS Marco. This is about 1 million or so Bing queries with a relevant web page for each one and then a non-relevant for each one. And that's about it. MS Marco is the name of the game. There really is no other collection that's this big so all the neural systems are trained off of MS Marco. They're coming along now with some other examples that are coming out. But at least until now, MS Marco is the name of the game. And here's an example MS Marco training example. So you have Bing query, foods that will help lower blood sugar. And you have one passage that's relevant to it and one that's not. And you have a whole bunch of these and you train your system on that. So how are you going to use these things? What kind of system are you going to produce? There are two main classes that we're going to talk about. The first is a cross encoder. And very funny. A cross encoder looks at a document in a query and tells you how similar they are. Okay, so the cross encoder is a trained neural system that is doing that task. And you always have to have a document and a query when you do that. Okay. So at training time, you're basically training the classifier, maybe modifying your language model and training the classifier. At indexing time, you take a break because you can't index because you have to look at every document. Right? Because the document has to be present at the same time as the query to get your score. Okay, so you can't really index it because you still, even if you index it, you still have to look at all the documents. Okay, then at retrieval time, you look at the document and the query. So this is very expensive, right? So when we have a re-ranking approach, we can use a re-ranking approach to exploit a cross-encoder. Okay, that because you do a retrieval, you get back with the top 10 documents or 1,000 documents or whatever you choose to, and then you apply the cross-encoder to each of those documents. Okay, and so then you have a score for each document, and you can rank them. The second type of system we'll talk about is a bioencoder. And the idea of a bioencoder is it's similar to a cross-encoder, but you don't have to have the document and the query present at the same time. So at training time, you just train up your language models to be able to produce a vector for a document and a vector for a query. And then at indexing time, you index all your documents. That is, you take every document and you calculate its score according to this, the trained model, okay? At retrieval time then, you don't have to have the document there. You just have to have the vector for the document somewhere that you can get at, right? So at retrieval time, you take your query, you run it through the language model, you get a vector or vectors. And then you have to be able to find the vectors for the documents, but you don't need the original documents. And there are reasonably efficient ways to find vectors when you have a bunch of vectors. Approximate nearest neighbors is the most commonly used one. The goal is you have a whole bunch of vectors and you want to you have some probe vector and you want to find all the vectors that you've indexed that are close to it. Yeah. Yes, so the question is, how do you store these vectors in a database? So this KD tree here is a common way to do it. I don't want to get into the details, but essentially you have a tree that that you can move down through and find the right. If you look at the lower right, there's these different areas that have different vectors in them. Find the right area and then look at those vectors in that area. So it's approximate because this isn't always right? You can have an area here, very close to an area here, and you have a vector here, and you're not going to find it because it's over here. Right? So you can either look in several different areas, or you can just cross your fingers. Right? It's approximate, but it typically works pretty well. And as I said, FAISS, F-A-I-S-S, is a commonly used package to do that. Okay, so let's look at a couple of particular bioencoders. Okay, DPR, dense passage retrieval, is a bioencoder that uses one vector per document and one vector per query. Okay. So at training time, we have our training examples, MS Marco, say, and training time we build our models so that we know how to produce a vector for each text. At indexing time, then we run our documents through there and get a vector for each document. So now we have one vector per document. And we store those vectors in our nearest neighbor index. Then at retrieval time, we run our query through it, get a vector. And we ask the nearest neighbor index, oh, show me all of the vectors that are near this one. And so that gives you a list of vectors. And then you apply your similarity metric to those two vectors, maybe cosine, to rank them. Okay. So that's dense passage retrieval, and it works reasonably well. It's works better in English than in some other languages, but it is reasonably efficient because you only have one vector for every document. So that's DPR. The other bioencoder we'll look at is Colbert or Colbert. Nobody knows which is the correct pronunciation. Colbert is a one vector per token approach. Okay, so you're going to take your document and your query, break them down into tokens, and each one of those tokens is going to get a vector. Okay, so at training time, then you're going to take your MS Marco and use it to train your model so that at indexing time, you can convert a document or a query to a set of terms. In this case, the document. So you take each document and you convert each document to a set of vectors. And then you throw those all in your nearest neighbor index. So that at query time actually has two phases. In the first phase, you're trying to figure out which documents to score. And in the second phase, you're scoring those documents. So in the first phase, we're taking our query, we're converting that to a set of vectors. And for each vector, we look it up in our nearest neighbor index and find all the vectors that are near it. So in the upper right here, this is the result of that. We find our queries about antique walking canes, and we say, oh, antique is in these documents, walking is in this document, and so on. Okay, so that's how we know which documents to score. And then we use that maxim score to compare the bag of vectors for the document to each document to the bag of vectors for the query. Okay. So this is pretty much the state of the art bioencoder. The systems that are more effective than this typically combine several different systems. So this is, this is essentially the state of the art for a bioencoder that's just by itself. Questions on how this works? Yeah. Okay, so why is token by token indexing better than one vector per document? And I think it's just that you can express more subtleties about the meaning if you have multiple vectors, right? If you have only one vector, then you're limited in what you can express, right? Because you only get one point in this vector space, right? Whereas if you have one vector per term, then you how to express this? Well, I can't think of it, but basically you just have more information to work with, right? You have more bits of information about what the meaning of the document is in the query. And so instead of just matching one point, if you can match all of these points, that's going to be better than just having a match. Think of it this way. If you took the Colbert approach, one vector per term, and you took the centroid of all those vectors in the document and the centroid of all the vectors in the query, you would essentially have a DPR system, right? But taking that centroid, you're losing a bunch of information about where exactly in the space you are. Okay, does that make sense? Okay. So these are our main two architectures, a bioencoder and a cross-encoder. And the cross-encoders have higher effectiveness, but the bioencoders have higher efficiency. So what we really like is to combine the efficiency of the bioencoder with the effectiveness of the cross-encoder. So we need a different way to train this, and we're going to use distillation for that. If you haven't heard of distillation, basically distillation uses a very high quality model to teach a lesser model. So here we have a bioencoder that we'll call the student, and we have a cross-encoder that we'll call the teacher. And what we're going to do is use the cross-encoder to score documents, and then we're going to try to teach the bioencoder to match those scores. Okay. And the way we do that is using KL divergence. KL divergence, if you recall, measures how close two distributions are to each other. And what you do is you take one of your training batches and you score all of the documents in that batch. And then you give the same batch to the bioencoder and say, here are the scores. Use as your loss function the KL divergence between the scores you're assigning to this set of documents and the scores that the teacher assigned to it. And you try to reduce the difference between those two. Okay, so this is a teacher-student approach, a distillation approach. And with this approach, you can get performance equal to a pre-GPT-4 cross-encoder in a bioencoder. So it's a very effective technique. Okay. So as long as you have a cross-encoder that does a really good job, then you can typically match that score. So, well, I'll talk about that later. Yes.
So, just to get it better, what are the targets? You said the distribution, so that's the distributions over the target documents, which I'm trying to like. What is the output of the bioencoder? The distribution from to the documents, right? Or
so the bioencoder is trying to score each document, right? So you're trying to teach it how to score a document. Okay, so you use a cross-encoder. You have a batch of a bunch of training examples. You have the cross-encoder assign a score to each of those. That's a distribution over those.
Okay, so my question was, what is the distribution over? So it's over the documents given the query.
Yes. Oh, yes. Over the documents given the query. Yes.
Try because again in Vision we do this also, but it has been found that for classification, it's better to not use KL divergence to emulate the distribution over the classes, but rather take the hard distillation, like just take the argmax of the distribution and use it. Has this been tested?
I believe that does not work as well as the KL divergence. Okay. Yeah, I'm pretty sure of that. Yeah. Yeah, that's been tried. That's interesting though that it's
maybe it's though because we are dealing with classification, right? So we want to find one best class. In this case, maybe I don't want to lose the nuances.
Yes.
Right?
Yeah. This is not a classification. Yeah. Okay. Cool. Okay. One last approach is ensembling. In ensembling, you take a bunch of different systems, run them all, get a rank list out from each one of them, and then you combine those lists. All right. And the most common way that's done is with what's called reciprocal rank fusion. And basically, you are looking at the rank of a given document in each of the lists and use the reciprocal of that rank to the sum of the reciprocals of that rank across all the lists to score that document, and then you order them by that score. Okay, it's a very simple combination. It's fusing on rank is almost always better than fusing on score, because for any system that produces score, it's hard to know what that score is really meaning. It's hard to calibrate it against other scores. So although one would think that a score would give more fine-grained information than a rank, in practice, rank-based fusion almost always works better. We have an evaluation called Nuclear, which is a cross-language retrieval task. And it's run a couple of years. For this past year in 2023, this is the architecture of the top performing system. So it uses an ensemble of 14 different methods. Okay, so it runs 14 different retrieval systems and combines the results. And it does that it uses 7 different retrieval systems, including statistical and neural systems. And then it fuses those, and then to produce the top 1,000. It takes the top 1,000 documents from each one of those. You get 1,000 documents, and then you run more systems and take the top 30 off of those. Those systems are more expensive because you only have 1,000 documents to look at, not the entire collection. And so then you get it down to the top 30, and then you ask rank GPT-4, you use an approach called rank GPT-4, which is basically saying, hey, GPT-4, what order should I put these 30 documents in? And if you do all that, the rank GPT-4 only adds a little bit of effectiveness. We have all these different systems here, and together they do a pretty good job. You just get a point or two off of GPT-4, but that is how the top performer by effectiveness in this evaluation works, right? And most of the evaluation that we're going to see is by effectiveness. Efficiency in these evaluations typically doesn't come up, but we'll talk about that in a minute. Oh, here's how rank GPT-4 works. Essentially, it's doing sort of a bubble sort. It's trying to re-rank 30 documents. You can't put 30 documents into the input buffer for GPT-4. So you can do 10. So you put the last 10 in, it re-ranks those, and then you throw away the bottom 5, take the next 5 here, re-rank those, and so on. You just keep doing that until you get to the top. It's not a particularly smart way to do it because you're doing a lot of comparisons, and a really good document or a really bad document here can't drop too far down the list. So there are going to be, this year, there are going to be better ways to do it. We're working on one, but that's basically how folks are using a really large language model to do this, to re-rank a small set of documents. Okay, this is where we're supposed to break. So any questions there? Okay, now you know everything about neural information retrieval. Here's where we are. Now, it's very important to talk about evaluation and information retrieval. Information retrieval is basically the grandparent of open evaluations. The Trek evaluation started over 30 years ago, and it has driven the field. These evaluations have really driven almost everything in the field that isn't driven by web search engine. And since the web search engines tend to be proprietary and there's not a lot of insight into what's happening there, academics have focused on stuff that's open, and so the evaluations have really driven that. You can evaluate for efficiency or effectiveness. For efficiency, there's just very little agreement on how to measure it. You can look at wall clock time or CPU time or GPU time or response time or indexing time or index size. So there are a lot of measures of efficiency. And by and large, the evaluations look at effectiveness and assume that efficiency will be handled after you have an effective system. So for effectiveness, we want to know how well one approach to retrieval compares to another, okay? And there are at least 3 requirements that you have if you're going to do a score-based method for doing this. You need an evaluation collection that has documents and topics. You need an answer key that is, it says for each topic, what documents are relevant. And you need a way to score a result based on the answer key. So you need some metric. Okay? The goal in measuring the effectiveness of information retrieval is not to tell you how good a system is. Nobody tries to say, oh, your system is this good. Like blue score for MT, it's essentially trying to tell you how good an MT system is, right? Because if you have a blue score of 7, you're not going to be able to read much. If you have blue score of 50, you know you're going to be able to understand the output pretty well, right? So that's trying to learn how well an approach works. In information retrieval, we only ask, is this system better than that one? We do not try to identify how good a system is on some scale. And that has, pardon me, that has important consequences for evaluations, which we'll talk about. If we think about efficiency and effectiveness, we can put those in a chart here where some measure of effectiveness is on the x-axis. Here we have latency, which means better is to the left. And on the y-axis is some measure of the quality of the result. This one is called MAP, or mean average precision, which we'll talk about. Better is up here. So the ideal system would be somewhere way up above here on the upper left-hand side, where you get very good performance with no latency. Okay? And the relationship between effectiveness and efficiency is not a single value. It's a frontier, right? And here we have a Pareto analysis of a bunch of cross-language retrieval systems. And you can see that you might choose to be at any point along this frontier, along this this dotted line, right? If you really care about latency, you just can't afford any latency at all, you're going to take this system called PSQ, and your effectiveness is not going to be not that high, right? If you want more effectiveness and you can afford it, you can go to someplace here where you get 30% better effectiveness, but your latency is higher. All the way up to systems like this. Now, no, it's not. Okay. I'll point out, well, I won't point that out. Okay, that'll come. There is an evaluation paradigm called the Cranfield paradigm that has been the mainstay of information retrieval evaluations since the 1960s. That's Cyril Cleverton down there who invented it. Cranfield is the place it was invented. In the Cranfield paradigm, you have a bunch of documents. You throw them into your search engine. You have some topic. You convert that to a query. You throw the query against the search engine, and you get back a ranked list. Then you have relevance judgments that tell you which documents are relevant to which topic. And you combine those using the score evaluation. So this is the Cranfield paradigm. Okay, and we'll get into some more details of it. But this is how most of the information, ad hoc retrieval information system evaluations have worked. So these are the main bits that you actually have to build to have a Cranfield evaluation. You need topics, documents, and relevance judgments. So we'll talk about each of these in turn. Okay. In the evaluation, you're going to run this over many different queries across many different search engines. And you're going to combine the results and say, oh, overall, over all these queries, search engine C had a better score than A or B. So we're going to crown engine C as the most effective system. Okay. Remember, our goal is to distinguish systems. So we don't know what this means in terms of effectiveness. And in fact, it could be that system C is really good on this kind of query and really horrible on this kind of query, right? We don't care. We have a set of queries. It's overall performance across all the queries. And we've crowned C here, okay? So we're trying to distinguish systems here. So let's look at the documents first. There are lots of challenges with documents, lots of features of documents that make retrieval interesting or difficult. Presumably you're modeling some task, right? You actually have a user. You've tried to keep them behind the curtain, but they keep sticking their nose out. They have some tasks they're trying to do. And so really the documents are going to reflect that task, right? So if you're trying to build a web search engine, the documents in your evaluation collection really ought to be web documents of the type that you want to be able to retrieve, right? If you're trying to retrieve over medical abstracts, then you want your documents to be from that domain. You have to name your documents. You have to worry about encodings and language ID. The size of the document collection is important. If you have 500,000 documents in your collection, the techniques that work well are going to be different from the techniques that work well for a 5 million or 10 million document collection. Okay, so really the size of the collection is important. How long the documents are is important, and whether you have to chop them up into pieces or not. Document stability. Do the documents stay the same over time, right? Like in a web engine, a web page might change a lot over time, right? So it's not a stable document. And if you want to have an evaluation collection that's a static collection, you're going to have to freeze that at some point. And document presentation, how you're going to actually show the document to the user. So there's a lot of challenges with documents. To build this collection, including deciding which documents are relevant, you're going to have human assessors in the Cranfield paradigm, okay? There is work in trying to use an LLM as a substitute for a human assessor. People have reported very good results with this. NIST has tried to replicate it and says it doesn't work. So this is very new work, and it's not clear to what extent an LLM will be able to replace a human. But humans have two tasks: topic creation and relevance assessment. So in topic creation, you've picked your document collection, you try to create topics that will have some relevant documents in the collection. And once you've built those topics, then you have to assess for each topic which documents are relevant, right? So somebody has to sit there and say, yeah, that's relevant. No, that's not. The assessor has to understand two things. They have to understand the retrieval task, what it means to retrieve, what relevance means, and so on. And they have to understand the topic area. So if you were, like one of the things we're doing in our evaluation of cross-language retrieval is we're trying to retrieve over Chinese scientific abstracts. So we have a big collection of scientific abstracts in Chinese, and we have English queries. And we want to build a collection that lets us assess how well a cross-language system can retrieve the right abstracts based on a query here. And the challenge there is that the scientific vocabulary is very different from general vocabulary, and it makes the language models that you use much less effective. So how do you deal with the fact that you have all this scientific terminology in two different languages? If you want to build that collection, your assessors have to both understand the retrieval task, and they have to understand the content of the document. So we're actually building a collection where we're getting PhD students, mostly from Hopkins and College Park, and asking who have to be native Chinese speakers and hopefully trained in their scientific area in China, not here, so that they understand the Chinese vocabulary for these things, which sometimes is the same as the English and sometimes it's not. And we get those, and then we sit them down and try to do this task. Say, make up a query, find abstracts that are relevant, judge whether they're relevant. Okay, and so your assessors have to understand the topic and the task. So you have to train them. If you're going to do this, you have to train your assessors. You can't just say, oh, here, Mechanical Turk, do this. I mean, you can use Mechanical Turk, but you still need training, and you need more assessments to get a high quality collection. Oh yeah, this is what I was saying. LLM is assessor. People are trying that, but as I said, NIST has yet been unable to replicate the success that have been reported in the literature. And So NIST, the National Institute of Standards and Technology, is in the Department of Commerce. It's responsible for setting, for basically evaluating, setting metrics and evaluating things. And NIST runs TREC, the oldest retrieval evaluation that's been going on for over 30 years. And so they're very interested in, if they could build a collection without having to pay assessors, they would love that, right? So they want this to work, but it hasn't yet. Okay, so that's the documents. Let's look at the topics and the queries. The assessor has to build topics. Here's a sample TREC topic. So as I said, TREC is the evaluation that's been running for many years. And you get topics that have SGML markup, and they have three different pieces. They have what's called a title, which is just a short phrase, 2 or 3 words about the query. You have a description, which is a sentence length description of the information need. And then a narrative, which is essentially a description of what is relevant and what is not, that an assessor might use to assess the topic. So that's what TREC topics look like. This is not a query, okay? This is not something that you can take and throw into your retrieval engine. You have to convert from this information need, from this topic, to something that your engine will recognize, right? So the way people typically do that for TREC is they'll either take just the topic, the words of the topic, and treat that as the query, or just the description, or the combination of both. Those are the most common ways people convert a topic to a query. And most retrieval engines will take a text query and find the result. So that's how that works. But you have to remember that different systems will produce different queries from the same topic. So what is a good topic? Well, you want not too many relevant documents. If a topic has many, many relevant documents, then any system is going to be able to find them, right? You can do some horrible system, and it'll probably find a bunch of them because there's so many. And so you won't be able to distinguish the good systems from the bad ones. You also don't want too few relevant documents, because if you have very few relevant documents, small changes in the ranking can produce large shifts in your score, right? A system that ranks this relevant document in first place compared to a system that ranks it in second place, the first place is probably, given your evaluation metric, it's probably going to look way better than the other one, when really there's not that much difference in them. There's just one position off, right? And you get quantization issues when you have very few topics, that you can't produce many gradations in your scoring metric. You're stuck with a very few different levels of difference. How many topics do you need? Well, in the standard type of evaluation, like this TREC evaluation, where you saw the topics there, you generally need 40 or 50 topics to have an evaluation that can produce statistically significant difference between two systems. If you're doing something like a known item retrieval task, where you only know one relevant document, like if all you had was MS Marco and you had one relevant document for each topic, then if you were using that as your evaluation collection, then you have to use many more than 50 queries to be able to distinguish systems, because you don't know about all the other relevant documents. So you have to take into account the fact that you don't know what the other relevant documents are. So that's what an assessor has to do when they're building a topic. And then they have to do relevance judgments. And as I said before, relevance is an opinion in information retrieval evaluation. Whether this document is relevant to that topic is the opinion of the assessor, okay? We don't say it's truth. We just say it's their opinion. And assessors disagree, right? If you gave the same documents and topics to different assessors, they're only going to agree about which ones are relevant maybe 90% of the time. Okay, they just don't agree. So you can't come up with some real true ground truth gold standard that is the absolute answer, right? You have to have simply one person's opinion of the relevance. And that's why when you build these collections, you always want to try to have the same person develop the topic as assesses the relevance of the documents. And since you have to, typically for an evaluation, you develop the topics, then you give them to the systems and you wait 3 months, and then you have the scores, the documents to score. There's a separation between the timing of the topic creation and the assessment of relevance. You really want to have the same person doing those two, because they have a notion of relevance that's in their mind that you're trying to model. And the fact that different folks disagree over what's relevant, if you were trying to get an absolute score, how well, on a score of 0 to 100, how well does the system perform, right? That's going to throw a wrench in all that, right? But if you care only about, say, asking whether this system is better than this system, then that's not nearly as much of a problem, right? You have, because, over a bunch of queries, the difficult, I'm trying to say this, the same problems are affecting most systems the same way, right? So if there's some document that you would say, oh, that's relevant, right? But the assessor said, no, that's not relevant, right? And then your system returns that document in first place. Says, well, this should have been marked relevant, right? And yeah, if you wanted the absolute score, you'd have a case. But the other system also has that problem that that document is marked as not relevant when it maybe is, right? So the two systems face the same problem. So it doesn't affect the ability to distinguish systems nearly as much as it affects the ability to get a real score, an absolute score. And NLP applications don't like that, right? This idea of opinion, just you try to sell it to NLP folks, they're like, what are you talking about? And like if you're building a bunch of parsing examples that you're going to test on, people try to have the exact right answer for what each parse is supposed to look like. Here we don't care so much. Okay. You can have either binary judgments like this is relevant and this is not, or you can have different levels. Most of the collections that are out there have only binary relevance judgments. It's very difficult to get consistency on graded relevance judgments, not only across assessors, but within one assessor. You ask the assessor one time, how relevant is this? And they say, oh, this is very relevant. And then, next month they say, well, it's not that relevant. So there are systems that use these graded relevance judgments, but most of the collections don't. Relevance judgments are always expressed in what are called QRELs. This is the TREC format for expressing relevance. They are white space delimited, one document and query per line. The topic ID is the first column. Second column is unused for historical reasons. You just make it 0. The third column is the document ID. That'll be whatever document ID that you're given as a collection. Here it's just some number, but it could be document 42 or whatever. And then the relevance judgments are last. If you have binary judgments, you'll just have 1s and 0s. If you have graded judgments, you can have different numbers here. So like here, the this document here is judged highly relevant. This one is judged somewhat relevant. So when you hear QRELs, that means relevance judgments. Okay, and that's everybody talks about them that way. Let's see. We got to go on. We're going to skip this. Dumpty. All right, let's look at metrics. Okay, we have about 10 minutes to look at the various metrics. There are a bunch of metrics you can use. There are efficiency metrics, but as I said before, they're hard to standardize, and they're not typically an evaluation might say, oh, please report these numbers if you can. Some people can, some people can't, you know. How many GPUs did you get when you're running, you know, I don't know, whatever the scheduler gave me. So some of these are hard to know. It's the effectiveness metrics that are most paid attention to. And there are many, many effectiveness measures, and we're going to go over probably the 4 most commonly used ones. Precision and recall is, let me see this. Precision is for the documents you retrieved, what percentage of them are relevant? Okay. So if you look at, say, the top 10 documents in your ranked list, and 7 of them are relevant, 3 of them are not, then your precision is 70%. Recall is what percentage of the relevant documents did you actually find? Okay. And if there are 4 relevant documents, and in your top 10 you found 3 of those, then your recall is 75%. You found 3 out of 4 of them. Okay. So the formulas are here for precision and recall. Yes.
Practical application for information retrieval. We seem to, or at least in our local thinking about things, we seem to care more about precision rather than recall. Given the hypothesis that the user does not know which documents is missing, but he understands if the retrieved documents are relevant or not. Is this something like generally agreed upon?
Okay, the question is generally agreed upon that precision is more important than recall? No, absolutely not. In many cases, that's true. In the legal domain, recall is really important, right? If you're doing like patent law, you want to be pretty sure that you found all the possibly relevant patents, right? So their recall is very, very important, and precision is not as important because you have to go look at as many documents as you can to get the right level of recall. Okay, so it really depends on the application. You can always build a system with 100% recall. At least I can. Maybe you can. What do? You give me the query, I give you back all the documents, right? Every single document. Oh, here they all are. 100% recall, okay? You can always get pretty high precision. Typically, if you have a decent system and you just return the top document, right? Your precision there is probably going to be very good because you have a good system and the very first document is returning is good. So you can't really talk about precision and recall independently, right? You have to have some balance between them. The F1 measure is a measure of, it's the harmonic mean of precision and recall. And F1 means that you're weighting precision and recall equally. So if you have, if you're doing F evaluation and you're okay with recall and precision being equally weighted, you use this, but you can crank up the importance of precision or recall here if you want. So that's F1. That's used for a lot of things, not just information retrieval, but named entity recognition and so on. These are metrics on sets, but we really want to evaluate ranked lists. You can't really know the true recall in most cases unless you look at every document. They're measuring different aspects of retrieval. And so some sort of combined measure can be more effective. So here are the combined measures that are typically used. Mean average precision. Average precision is the average precision of your ranked list as you look deeper and deeper in the ranked list. Okay. So here we have topic 1. We have the first relevant document is given a position 2. Okay, so there our recall is 25%. Let's say there are 4 relevant documents. And precision is 0.5 because at that point we have 1 relevant and 1 non-relevant. Okay. We then look down to the next relevant document and we say, oh, here we've we're at 5 retrieved documents. 2 of them are relevant, so our precision is 40%. And we found half of the 4 relevant documents, so our recall is 50%, so on. So you do that, you get the curves like you see on the right, some other examples. So average precision is how many evaluations will evaluate a single topic. Mean average precision looks over many topics. So you just average across all your topics. You have 50 topics. Your mean average precision looks like something like this. But people just talk about a single mean average precision score. What it really looks like under the hood is this. You have a bunch of, each of these lines is a different topic, and you have a bunch of topics. And some of them your system does really well on, and some of them it crashes and burns. This is the standard way these are laid out. Recall is on the x-axis. So as you look down the x-axis, you're looking deeper and deeper into the results. And the y-axis is your precision, up is better. So you can see that mean average precision, while it is probably the most commonly cited overall metric for a system, it is hiding a lot under the hood. Finally, NDCG. This is normalized discounted cumulative gain. NDCG is a measure that tries to add a few things to your retrieval. Discounted cumulative gain looks like this. And the idea, one of the ideas is that you can handle graded relevance. With mean average precision, you can't do graded relevance. A document is either relevant or it's not. With NDCG, you can get graded relevance because the numerator is the sort of the relevance level, and you have to assign some score to each relevance level. So maybe highly relevant, you give a score 3, somewhat relevant, give a score 1, not relevant, give a score of 0. So it handles graded relevance. It rewards early precision by making the denominator for the documents at the early ranks being smaller than those at later ranks, right? So it's weighted towards the beginning of the list, but it can incorporate recall. You can go out as far as you want and score this. Now, often you'll see something like NDCG at 10 or at 20, meaning that they cut it off at 10 or 20 documents and don't worry about the rest. And that's, in many cases, you care most about the top 10 or 20 documents. The ideal score would look like this. You'd find all of the highly relevant documents first, and then all the somewhat relevant documents, and then the non-relevant documents. And if you got the DCG score for that, that would be your best possible. So NDCG is just the normalization of your DCG score by the maximum possible score you get. Okay. Finally, recall at K. How many relevant documents you get at a certain level. So you run a system. How many, what's your relevance, what's your recall at 1,000 documents? And the reason this is an important measure is for re-ranking systems. You want the first system to have the highest possible recall within the number of documents that you're going to give the next system, right? So recall at K is another important measure that you'll see. Yep.
About the precision, you stopped after you recalled 3 documents, but the precision should go up until you find all the relevant documents.
Yes, but most evaluations don't require all documents to be ranked. Usually you'll say, most evaluators will say, give me the top 1,000 documents, right? And for many queries, you're not going to find all the relevant there. So yeah, you're right. If you went all the way down, you would get all recall levels. But if you only go down to 1,000 because the evaluation only demands that, then you won't.
Thinking about the distinction between recall at K versus average precision, since they are quite similar.
Well, not necessarily. I mean, if I have all the relevant documents at 950 to 1,000, those ranks, right? That's going to look horrible from a mean average precision, but it's great at for recall at 1,000, right? You really only care. You don't really care how they're ranked within there, right? if your only job is high recall. Okay. We have -1 minute, so there's this text retrieval conference that's been run, that there's a lot of things there. And that's how everybody judges how well their systems are doing. And if you really want to do something fun, you propose a track to track. Like the really fun stuff is what we're not going to get to here, which is cross-language retrieval. That's just really fun. And so we're running this track on that. But anybody can join these evaluations. You can sign up and put your system in. And I recommend everybody do some shared task like this at some point. It doesn't have to be information retrieval, but having experience doing a shared task like this is very fun and very educational. Okay, we're going to stop there because we're out of time. And if anybody wants to know about cross-language information retrieval, I'd be happy to talk with you about it later. So, thank you.